I'm pleased to introduce Daniel Reeves from the University of Michigan. He just finished his PhD with Michael Wellman on e-commerce and game theory, and he's going to be talking about some of his thesis work today. Daniel.
Thanks, Subbu. Okay, so you're all presumably here to learn about how to generate trading agent strategies. I'm going to spend most of the time on analytic methods for infinite games, but I'll also tell you about the empirical methods for large games. Everything I'm presenting today is joint work with my advisor, Mike Wellman. And there are some pieces, especially towards the end when I talk about the killer app for all this trading agent strategy generation methodology, the trading agent competition. There are several teammates and co-authors for that work. Okay, so first the big picture. My grand research vision and the ultimate goal of my thesis work is a strategy generation engine that reads in a description of a game consisting of game rules and a distribution from which private information is drawn. And it outputs a strategy, which is a program that takes actions based on private information and observations about the other agent actions. So in a sense, the goal is a program that writes programs that play games. Although I'll focus almost entirely on games that involve auctions of one kind or another, the framework is applicable to more general kinds of games. But before I say more about games, let me say what I mean by a game. It's really any circumscribed interaction between multiple agents where each agent is trying to maximize an objective function that depends on the interplay of the agent's actions. The agents here are captured by their strategies. That's the output of the strategy generation engine. And I've depicted here a one-shot game. In a multi-stage game, agents perform actions and then learn something about the other agent's actions. And then that becomes part of their information before performing the next action. The whole eventual action history plus the private information informs the payoff function. And we assume a finite number of rounds. By infinite game, I'll mean that there are infinitely many possible actions. For example, bidding a real number. If there's any inherent randomness in the game, that's captured by a dummy player, nature. The player's private information is also known as their types or preferences. For example, in poker, your hand is your type. In an auction, it would be your valuation of the good being sold. The output of the payoff function is, of course, the payoffs, or the utilities of each player. So agent 2 did not fare so well here. If an agent only has one possible type, then that would be called a game of complete information. But in general, we're talking about incomplete information games. This captures the case that I may not know what your payoff function is, but we assume that if only I knew your private information, then I would know. So we always assume that the global payoff function, as well as the probability distribution from which the types are drawn, are common knowledge. And common knowledge is actually a hairier assumption than it sounds. If you're not sure why, ask me about blue-eyed monks afterwards. But otherwise, this can be a quite realistic model of real agent interactions. And I'm mostly talking about artificial agents, but this can be applied to humans too. And in fact, game theory is even useful in biology. In that case, not so much for advising clever squirrels on hoarding strategies, but as in describing evolved strategic behavior in nature. Okay, a few more key definitions. My best response strategy is my optimal strategy, the one that maximizes my payoff, if I knew everyone else's strategy. Nash equilibrium is just a profile of strategies that are each best responses to the others. Nash himself proved that for any finite game, as long as players can use mixed strategies, that is randomized between their actions, then at least one Nash equilibrium must exist. A Bayes-Nash equilibrium is the natural generalization where players are simultaneously maximizing their expected payoffs given the strategies and the known type distributions of the other players. By expressing a possibly multi-stage game by enumerating the possible strategies, any game can be converted into a one-shot game of complete information, and that's called the normal form of the game. And finally, almost all the games I've studied are symmetric, and that means that ex ante, before the types are determined, all the players are identical. For example, we might assume that there's nothing to distinguish different poker players until the hands are dealt. A symmetric profile is simply a homogeneous one. All agents play the same strategy, which in a symmetric game we might well expect they would. Symmetric equilibrium, then, just refers to an equilibrium profile that's symmetric. Nash also proved that symmetric games have symmetric equilibria. And one last definition, the epsilon of a profile is how much better I could do by playing my best response to the profile instead of what the profile actually dictates. So that's 0 if and only if the profile is a Nash equilibrium, and it gives us a measure of how far from equilibrium we are otherwise. Any questions about any of these game theory concepts? And I'll move to the meat of the talk. Okay. Here's what you've really come for. I'll first describe my analytic approach to generating best response strategies in a class of one-shot, two-player infinite games of incomplete information, and use that to find Nash equilibria. And that works for many simple games. I'll give you examples of those. For more complicated games, I'll describe the empirical approach. And it's applicable to two monster games in particular, the trading agent competition and simultaneous ascending auctions. And I'll talk about those briefly at the end. So here's our class of two-player one-shot infinite games of incomplete information. The type distributions must be piecewise uniform. So that captures pretty general type distributions. The payoff functions of my type and my action and the other agent's type and the other agent's action are of this particular form, where these Greek letters are all parameters. So that class of games turns out to be pretty general and captures really most two-player one-shot games that you can think of by appropriate settings of those Greek letters. Here are the parameter settings for a host of games, some well-known like first price and second price sealed bid auctions, and a couple we made up, namely the shared good auction and joint purchase auctions. I'll describe those shortly. Okay, so games can now be described by a set of parameters. And if we also specify a piecewise linear strategy like this, and remember, in a one-shot game, a strategy is just a mapping, one-dimensional mapping from type to action, then we're ready for my main result for this game class. Okay, namely that for payoff matrices of this form, this parameterized form, along with a specified type distribution and a piecewise linear strategy of this form, then we can compute in polynomial time the best response strategy, and it's also a piecewise linear strategy. So just to give you the barest taste of what the proof of that theorem is like, we have a function that gives our payoff in terms of our type and action and the other agent's type, right? We're assuming a known strategy for the other agent. The other agent's type is a random variable from a known distribution. So we need to find our own action expressed in terms of an arbitrary type for ourselves that maximizes our expected payoff. We're maximizing that expected value. So in the complete information case, you could then apply any kind of numerical maximization technique and get your best action. But here we end up with this nasty expression involving t. But it turns out that the optimal action is always linear in t in any t neighborhood. So if we partition the type space in the right way, we end up being able to express the optimal action as such and such linear function of t if t is in such and such range, and such other linear function of t if t is in some other range. In other words, it's the best response strategy is piecewise linear, and it looks like this. Sorry, like this. So the great thing about this is that it means that we can now iterate this best response procedure and from some arbitrary seed strategy. And if we're lucky enough that it converges, in other words, reaches a fixed point, then we have a strategy that's a best response to itself and is a Nash equilibrium. So the theoretical result is the best response finding, showing that the best response to piecewise linear strategies is piecewise linear. So let's apply this to some simple games. A very simple example of a game in our class, kind of the canonical example, is a first price sealed bid auction. So in this game, the players' types are their independent private valuations. We'll assume they're drawn from uniform 0-1 distribution. And the actions are the bids. So your payoff is your valuation minus your bid if your bid is higher, and nothing if your bid is lower. And the winner is chosen at random in the case of a tie. In that case, it's the average of your type minus your action, your valuation minus your bid, or 0. So this game has a well-known equilibrium of shading your bid down by the number of players. So in the two-player case, bid 1/2 your valuation. That's the unique symmetric Nash equilibrium strategy. And my algorithm finds that equilibrium by computing iterated best responses from most seed strategies. For example, the best response to truthful bidding, where you just bid your valuation, is in fact this Nash equilibrium. Here's another game that we call the supply chain game. So we have two producers in series, a consumer that we're not treating as an agent. Only two agents are these producers. They each have the option to produce the output in their piece of the supply chain. If everyone does, if both these producers produce their output, then the final output of the supply chain is that G2, which the consumer values at V and will pay anything up to V for it. So the way the game works is that the producers submit a bid saying how much they want to receive if they're going to produce their good. As long as the sum of their bids are less than or equal to the consumer's value V, this all goes through, the good gets produced. And the payoff to the producers is their bid, what they get, assuming that the deal goes through, if the sum of their actions is small enough, minus their cost, which is private information to them. Okay, so this game was studied in a paper on supply chain formation by Bill Walsh and others, and they proposed a general strategy for a broader class of supply chains than this simple one. But for this simple game, their strategy works out to this. And as you can see, it has this nice piecewise linear form, so we can feed this published strategy to my best response finder, and we get the strategy in blue. And after a few more iterations of best responses, we seem to be converging to this green strategy, which is actually an equilibrium that after that original paper on supply chains was published, Bill Walsh and I derived this green equilibrium by hand for this game. And our algorithm, of course, if you put in this strategy, it confirms that it's an equilibrium, as it must. But that's not the equilibrium that we converge to when we start from that initial seed strategy from Walsh and company. Rather, we end up at this asymmetric equilibrium, which is basically the pair of strategies in which we each ask for half of V, approximately, unless that's not enough, given our cost, in which case we just kill the deal. So it's pretty easy to see that that's an equilibrium. If I know that you're asking for X, then I might as well ask for V minus X. Any more, and we're both going to get nothing, right? Sum of our actions has to be less than V for us to get anything at all. And if you're asking for X any less than V minus X, then I might as well have asked for more. So in fact, there's a continuum of equilibria of that form, although the iterated best response procedure here does always seem to converge to reasonably fair ones, where both agents ask for about half. Here's another game. This comes under the heading of public good or provision point mechanisms. I'll describe a variant that seems not to have been solved in the literature before. Namely, two agents want to jointly acquire a good that costs C, for which they have private valuations. They submit a sealed offer, and the good gets bought if and only if the sum of the offers exceeds that cost, C, in which case the excess is split evenly and given back. There are variations where the agents don't get the excess back, that's just lost, or where they don't get their contributions back at all. They submit their offers, and if it's not enough, they're out of luck. That's called the contribution game. Okay, both of those last two variations are in the literature, and they have very different equilibria from this one. This one actually is very similar to the well-known equilibrium for the bilateral bargaining game, also called the sealed double auction, which my algorithm also finds. I talk about that in the paper. And I wanted to mention, I've suggested that most two-player one-shot games that are in this class of games we're dealing with this particular parameterized space of games, of payoff functions. But one potentially useful one that isn't is a variation on this, where instead of splitting the excess evenly, we split it in proportion to how much we contributed, which is arguably a sensible thing to do. But that game, that variation on this, we cannot do. So this is just the one, and that's because that introduces some non-linearities in the payoff function for types and actions. But for this one, we can solve it. And this is the Nash equilibrium of this game. 2/3 your type plus C over 4 minus the sixth. So now suppose that we played that game and jointly acquired some good, but now one of us is leaving town, and we can't split the good in half, so we need one of us to buy the other out. So my friend and colleague Kevin Lochner and I first came up with this game to decide which of two roommates should get the big bedroom and for how much more rent that person should pay. And since then, we've actually used it multiple times to allocate undesirable tasks for which we've both had joint responsibility. It's actually a pretty useful mechanism. It's kind of like flipping a coin, but more economically efficient. Okay, the auction rules specify that each agent submits a sealed bid, as usual, and the high bidder gets the good but pays half their bid to the loser in compensation. So that's how the mechanism works. It was designed such that if you played truthfully, the surplus would be split evenly. But playing truthfully is not, in fact, a Nash equilibrium. But we can find it using the best response solver. We can give truthful bidding as a seed strategy. This is what happens. It's to essentially shade your bid down 2/3 of the way to the lowest possible valuation. And this is assuming uniform distribution on the private valuations between A and B. So there's a picture of it. So of course, a nice thing about having this game solver for humans using these mechanisms is basically we're leveraging the revelation principle and playing the modified game where agents submit their true types to the game solver. So this is this kind of metagame that has the solver wrapped around it, which then plays the Nash equilibrium on their behalf. So two people playing the shared good auction, assuming that they believe the type distribution, can simply submit their true types without strategizing at all. And this also mitigates the problem that we have no guarantee that the equilibria that the game solver finds are unique. But since the game solver finds this particular one, that makes this one focal, and if the new mechanism is you submit your true types, and it's going to play this Nash equilibrium, then by nature of Nash equilibrium, no one has an incentive to deviate from that. By the way, the plotted points here are with the error bars are simply from verifying the analytic results with Monte Carlo simulation. But I won't say any more about that now. One other game I wanted to mention is a variant of the Vickrey auction. The interesting thing about a Vickrey auction, or second price auction, it's called that because the winner pays the second highest price, is that truthful bidding is a dominant strategy. Dominant just means that it's your best response to every other possible strategy. So reassuringly, my game solver returns truthful bidding in the usual Vickrey auction for every possible seed strategy. But the variant is called vicious Vickrey because it adds a term to the payoff function for my utility for your disutility. So say we're competitors, business competitors, and I don't want to only maximize my profit, I want to minimize yours, right? So now I want to bid possibly more than my valuation in hopes that if I lose, I'll at least force you to pay more than you would have otherwise. Okay, so this turns out to be the equilibrium for that game, as you can see and this K is a parameter that says how much I care about your disutility. So one special case is the usual Vickrey auction where K equals 0. I only care about my own profit, and I don't care about yours at all. In that case, you can see that bidding your type is what falls out of that. And once again, my iterated best response solver can find that equilibrium for specific values of K, I should mention. Okay. To conclude the first part of this presentation, we have an algorithm for computing best response strategies in a broad class of two-player infinite games of incomplete information. We've used it to confirm many known equilibria in the literature, confirm some that we've derived by hand, and discovered equilibria in new games, like in the joint purchase and shared good auctions. The most interesting and useful aspect of this is, of course, not the actual best response finding, though that has its uses. For example, if you have a particular strategy that you think that the opponent's going to play, or for automating the proof of that a certain strategy is a Nash equilibrium. But the real win here is iterating this to find Nash equilibria from scratch. And it remains a goal to characterize that class of games. It may or may not be our entire class. In other words, characterizing when that process really will converge, because it's possible that it won't. Okay, what about games that have more than 2 players or have multiple rounds? In other words, most realistic games. I call them monster games because they're pretty much untouchable by standard game theory. For example, we're not going to find the Nash equilibrium of the full game of poker in the foreseeable future, although Nash himself and others have solved highly abstracted versions of poker. Or the problem of bidding in multiple simultaneous auctions, which is a problem we've looked at in a couple domains. Another one might be bidding for a set of Google AdWords. That would be an example of bidding in multiple simultaneous auctions. So I'll show you my general empirical game methodology, kind of a collection of computational techniques for finding good strategies in games like that. For all of these, I'll use a simple first price sealed bid auction again as an example and to help verify the methodology. Broadly, there's several parts to this methodology. I'll focus on the first few. The first is about determining a set of candidate strategies, that is, restricting the strategy space. This is the most drastic way in which we can cut monster games down to size. The next is game simulation, estimating the restricted game. Going along with game simulation, I'll talk about standard variance reduction techniques for Monte Carlo sampling, in particular the method of control variates, for which we've done some controlled experiments with first price sealed bid auction, FPSB, and also applied in the trading agent competition. Player reduction is a kind of complement to reducing the number of strategies, and it's another way to radically reduce the size of a game to make it more tractable. And without generally sacrificing too much in terms of solution quality. Once we have an empirical estimate of a game, we can apply various off-the-shelf techniques for solving it. I'll mention a few of those. And finally, I'll briefly talk about a couple methods for assessing how well the solutions to the empirical game approximate solutions to the underlying game of interest. And I'll focus on toy examples and then talk about the monster games at the end. So let's start with our old friend FPSB, which is by no means a monster game. In fact, it's been solved, as we know. But it has infinite type and strategy spaces and nonlinear payoff function. And so it has many of the attributes of games that are analytically intractable. So it's going to serve as a good test case. So I've already described the game. This is the two-player case. The generalization to n players is very straightforward. N of us submit a bid. The winner pays their bid. This time, the Nash equilibrium is to play n minus 1 over n times t. That's the 1/2 t in the two-player case. For our purposes now, we'll pretend that we can't deal with such a rich strategy space as all functions from type to action, right? All one-dimensional functions on 0, 1. So we'll restrict the strategy space by imposing the constraint that strategies must be of a particular parametrized form. Okay, in general, the way we do this is to pick a baseline strategy and introduce parameters that generalize it. For FPSB, the most straightforward strategy, although the worst possible strategy without actively throwing money away, is truthful bidding, just bidding your valuation. That guarantees you 0 surplus. But if we generalize that strategy with a shade factor k, then the strategy space now actually includes the real Nash equilibrium, n minus 1 over n times the type. If we didn't know that, we could have also included, say, a translational parameter b, or allowed a piecewise linear strategy with some finite number of pieces. And those are all ways to come up with a finite set of parameters to generalize the baseline strategy. Okay, but the point is, even if the baseline strategy is awful, as is the case for FPSB, as long as the space of strategies allowed by the parameterization includes smarter strategies, and they need not be identifiable as such a priori, then our methodology has hope of finding them. So as we'll see, introducing a shading parameter in FPSB without knowing a good setting for it allows us to approximate the unique symmetric Nash equilibrium of the game. First, I'll quickly show some theoretical results for this restricted version of FPSB with shading, before showing how we manage when the games are too complicated to admit any analytic results at all. First, we derived a closed-form expression for the expected payoff for arbitrary symmetric profiles and unilateral deviations. So this is my expected payoff for playing k sub I when everyone else is playing k. Remember, k is how much you shade your bid. Okay, maximizing that with respect to k sub I gives us a closed-form expression for the best response. My best response if you're all playing k. where that C is an expression of n and k. Anyone want to guess what that looks like? It starts with a cube root of n. Yeah. So anyway, from this last term here, we can see, have a k of n minus 1 over n is a best response to itself. So we can see that also that the Nash equilibrium in the restricted game is the same. That we've captured it. It's also the equilibrium in the unrestricted game, where you can play any strategy, any function from type to action. And with a bit more effort, we can show that that's the unique symmetric equilibrium, just as it is in the unrestricted game. We also derive an expression for the epsilon of an arbitrary symmetric profile. And remember that epsilon, it just means the greatest gain I can achieve from deviating from a certain profile. Right? This is if everyone else is playing the symmetric profile k, you're all shading your bids down by k, then that monstrosity tells me exactly what I should bid in response to that. And these x's are, again, that crazy expression from the last slide. So it's a little ugly, but we've got a closed form expression for it. So those results are nice for comparison, but we can't get any kind of closed form results for the real monster games. So instead, the next step is to further restrict the strategy space by discretizing the parameters. So here I'm discretizing the strategies in the 4-player restricted FPSB game by 40ths, yielding 135,000 some strategy profiles. Right? We could all bid truthfully, or I could bid truthfully, and you could shade down by a 5th, and you could shade down by a 4th, all the possible combinations of those, up to symmetry. I simulated 100 games for each strategy profile to construct the empirical payoff matrix, which we typically represent this way. Each column is a specific strategy profile. This is a much smaller version than the one with 135,000 profiles, which is a little hard to read. This graph here shows the epsilons for each symmetric profile based on that empirical payoff matrix, the one that we gathered from 100 samples per profile. Okay, this is enough to see that there's likely an equilibrium somewhere around 0.7 something, right? Where remember that when epsilon is 0, that's a Nash equilibrium. If we overlay the exact results from the previous slide, the closed form expression, we can see that this is in fact giving us a reasonable idea of the solution to the underlying game. And by the way, if you're wondering why all the plotted points are always above that exact epsilon, anyone, I don't know if that's obvious to people. So the reason is that the empirical epsilons are based on the sampling noise from the 100 samples. So since the epsilon calculation takes the max of a bunch of these noisy estimates, it's typically going to find one that's anomalously high, and that's why all those will be above the true epsilons. Okay, and I'll talk about reducing sampling noise next. But to get a more accurate estimate of the solution to this game using just brute force Monte Carlo, I just upped the number of samples to 36,000. And at this point, we still actually can't estimate the unique symmetric Nash with very high fidelity. But it's clear that anything in this range here is going to have very low epsilon in the underlying game. So it's going to be very close to an equilibrium. And in the sense, I'm saying close in the sense not necessarily of proximity to the actual equilibrium, but close in how much you could gain by deviating. That's the idea of an epsilon equilibrium. Okay, so this brings us to variance reduction. The idea of control variance, which is a standard technique for Monte Carlo simulation, is to adjust the sampled payoffs for luck. For example, in FPSB, we expect that an agent's valuation correlates positively with its surplus. If my valuation for the good is very low, then there's very little chance for me to make very much profit. If it's worth a lot to me, there's the potential that I can get it for cheap and make a big profit. So the higher my valuation, the higher my expected surplus. So what we do is just bump up an agent's payoff when it has a low valuation or type and scale it down when it has a high valuation, such that these positive and negative adjustments average out to 0. Then by sampling these adjusted payoffs, it will tend to take fewer samples to converge to a good approximation. of the true expected payoffs. And for any exogenously determined estimation function, g, and I'll explain exogenously in a minute, the average of the adjusted payoffs will always be unbiased, and it'll have less than or equal to the variance of the unadjusted samples. So for FPSB, we can derive a sort of best case control variable, namely the exact expected payoff for an agent of type t as a function of t playing strategy k against an arbitrary set of other strategies. And that's what these expressions give, and there's some special cases I've left off. But the point is we can derive that analytically for this game. So of course, in more complicated games, we're not going to be able to derive anything like that analytic result. But instead, we can estimate a function using machine learning methods. So for FPSB, with one-dimensional types, that's very straightforward. For example, we can just use linear regression. But in general, with multi-dimensional types, including other sources of randomness in the game, it may not be obvious at all how the random elements influence the payoffs. In fact, the dimensionality doesn't have to be very high at all before it becomes very hard to empirically determine meaningful relationships between types and payoffs. For example, imagine a game involving bidding for many goods with agents type being a vector of their valuations for all the goods. So depending on the specifics of the game, we might expect that the sum or the max of that vector of valuations to correlate with payoff. It would take a pretty sophisticated learning algorithm with a lot of data, in other words, lots of game simulations, to rival a simple linear regression from the max valuation or the sum of the valuations to payoff. So in other words, when we have some sufficient domain knowledge, such as knowing that the sum or the max is a good summary statistic, we introduce control variates manually. And we've done that for the trading agent competition and some of the monster games I'll mention at the end. Okay, returning to our FPSB example, this graph just gives a visual sense of the adjustment via control variates. These are CDFs, so the more squished together it is, the less variance. Just in the interest of time, I'll kind of gloss over this. That you get the point that introducing these control variates reduces variance. This is the kind of best case control variate for FPSB, the analytically determined one. And actually, we can even use for every single sample, knowing the types, we actually have a closed form expression giving exactly what the expected payoff is. So we can apply that control variate, and of course that will nail the true expected payoff every time. So that was just kind of a sanity check to put that one there. Okay, so this is the unadjusted one here. I'll leave it at that. And just mention some other variance reduction techniques that we haven't done these kind of controlled experiments with so far, but we expect them to be a big win in game simulation. So just to mention them in case anyone's taking notes on how to apply this methodology to your own monster games. Quasi-random sampling and importance sampling are ways to tweak the distribution of types that you're sampling from to reduce variance in the sampled payoffs. Adaptive techniques combine various methods and adjust the parameters for them automatically as you get samples. Implementations of all these techniques are available as part of the GNU scientific library. And I'll also refer you to my forthcoming paper on how to deal with nature when applying these results. Remember, nature is this dummy player that we use to introduce other elements of randomness in the game. Okay, the next method for taming monster games I call player reduction. And the idea is very simple. We can approximate an n-player game with one of, say, n over 2 players, where each player in the new reduced game gets to pick a strategy for 2 players. They pick one strategy for 2 players to play in the original game. Or in general, you reduce it down to p players, and q is n over p here. Since game size is exponential in the number of players, this can drastically cut an impossibly large game down to size. And we'll see it was critical in the trading agent competition to do this. That's an 8-player game before reduction. So now the question is whether the reduced game bears any similarity to the original game. And of course, in the worst case, it won't. we can make up pathological examples where the payoffs vary in any kind of erratic way you can imagine. But our hypothesis was that for many natural games, the degradation would be graceful. And that's borne out for FPSB. This is 4-player FPSB with the Nash equilibrium 3/4, and that's the epsilons for other strategies. If you just consider the 2-player version of it instead, that has, as we know, an equilibrium of 1/2. Those are the epsilons in that game. If playing the equilibrium in the 2-player game was your approximation, you can see you'd have a pretty lousy epsilon in the true underlying game. This is the 4-player game reduced to 2 players, the 2-player reduction. We don't have a closed form for the epsilons. We do have a closed form for the equilibrium. That's this. Sorry, that's the equation there. But the point is that both in terms of epsilon and in terms of actual proximity to the equilibrium, we're much better off with this 2-player reduction than the actual 2-player game. And we have some theoretical results to generalize that to any number of players. So we've proved that in FPSB, if you have an n-player game, but computationally you can only handle p players, then they're always better off with the p-player reduction than the actual p-player version, both in terms of absolute closeness and epsilon. And for FPSB, solution quality degrades monotonically with more severe player reduction. So those are reassuring results for FPSB, but of course we don't actually need to approximate FPSB. We can solve that for any number of players. So to further evaluate the quality of this reduced game approximation, we turn to other natural game classes of potential interest. Local effect games fall under the category of congestion games. For example, deciding what roads to take when you have to trade off taking the most direct route with the possibility that many other agents will choose the same and the route will be slower, hence the congestion. So just to summarize the conclusion, player reduction does well at approximating games in this class as well. And again, we find that the solution quality degrades gracefully with the degree of reduction. And I'll discuss player reduction in the context of the trading agent competition shortly. And it was very critical there in getting any kind of strategic handle on that game. OK, everything so far has been about estimating an empirical game. Once we have that, we have a standard normal form game with a finite payoff matrix, and we can apply any standard game solving techniques. Just to mention the ones we've used, Gambit is considered the state-of-the-art solver for finite games. But it doesn't exploit symmetry, so it often blows up on games that are otherwise very solvable. Replicator dynamics is one that does, and this idea of using replicator dynamics is not new to me and my colleagues. In fact, it originated as a model for how animals evolve towards Nash equilibrium strategies. But we're the first, to our knowledge, to apply it as a solution technique for large games. Just briefly, the idea is you create a big population of agents. Initially, so here we have 5 strategies labeled 16 through 20. They're initially represented equally in the population, 1/5 each. Each generation, you take a random sample from them, play them against each other, and then adjust their proportion in the population in proportion to what kind of payoff they get. And the nice thing about this is if this reaches a fixed point, the populations become stable. An evolutionarily stable strategy profile of strategies is a Nash equilibrium, that corresponds directly to a mixed strategy Nash. OK, finally, the last phase of our monster game taming methodology is assessing the solution quality with respect to the underlying game of interest, or at least with respect to the exact restricted game after reducing the strategy space and possibly the number of players. So to do this, we first need to estimate a distribution representing our belief over the space of possible payoff matrices, because the payoff values we get are based on simulation, and so we have confidence intervals on those. So I won't go into how we do that, but we come up with a distribution for the payoff matrices based on that sampling data. And then one method of sensitivity analysis is to just see if enough samples from the payoff matrix distribution all yield the same equilibrium, in which case we can conclude that our equilibrium results must be fairly robust to sampling noise. So one way to operationalize that is to repeatedly sample payoff matrices, compute one or all of the symmetric equilibria, and then observe the empirical distribution of those equilibria. And so that's what this represents here. These are CDFs on those mixture probabilities from this game here. So we can see that for this particular exact payoff matrix, or our max likelihood payoff matrix, in other words, what we got from actually sampling, has 16 ending up with 0.7 something in the population. This tells us that there's some non-negligible confidence interval around that. We can do the same exact thing for epsilon, sample from the payoff matrix distribution, compute the epsilon of a particular profile. So this is just a histogram of those epsilons. This is from a different game, but we can say, looking at this, 15% of this probability mass is at 0. That means based on the sampling we've done so far, this profile has a 15% chance of really being in equilibrium. And maybe that means we want to do more sampling to become more confident that it's in equilibrium, or maybe it's good enough that the epsilon is very likely to be less than 400 in this game. This is $400 in the trading agent competition, which actually is pretty significant, so we probably want to do more sampling here. Okay. So to conclude the monster game taming methodology portion before, and then I'll just mention briefly the real killer apps of this, the trading agent competition especially. We're restricting the strategy space, we're reducing the number of players, we're simulating game outcomes, and that's where we use the variance reduction techniques to speed that up drastically. Then we analyze the empirical game, and then we assess the solutions to the underlying real game. Okay, so onto the real application of monster game taming. We, meaning our research group, my advisor and I and other students, created the trading agent competition travel shopping game in 2000, and it's been growing ever since. The whole research community is built up around this, a large body of literature. It's a really interesting domain for testing out trading agent strategies. Starting in 2002, the Swedish Institute of Computer Science took over the actual running of the game, and so we've been competing in it ever since. The game pits 8 travel agents against each other, all trying to put together travel packages for hypothetical clients. Does anyone know about the trading agent competition already, other than John? Oh, a couple of people. Okay. So I won't get into the intricacies of the game except to say that there are 28 simultaneous auctions that the agents are bidding in, auctions of various different types, flights, hotel rooms, entertainment tickets. One of the key strategic issues is the strong complementarity between the hotels. If you have a client staying in the towers, that's the hypothetically nice hotel, on day 1 and they don't leave until day 3, then that first room is useless to you unless you also get a room in the same hotel on day 2. You have to keep your clients in the same hotel for the length of their trips. So that introduces complementarities between these goods. And actually, it's a bit messier than that, since you may be able to shuffle your clients around, shorten their trips if you haven't bought their flights yet, et cetera. It's all sorts of interesting optimization problems underneath this. But fundamentally, we have a problem of bidding for complementary goods in simultaneous ascending auctions. And the other domain that we studied just distills that problem out, and we call that simultaneous ascending auctions, SAA, just a very abstractified version of the simultaneous auction situation. Okay, the name of our agent is Wolverine, from the Michigan mascot and the 19th century French economist Walras, because the first foundational idea of our agent was to predict market prices using a simple market model, namely Walrasian equilibrium. The reason price prediction is important is because of that exposure problem. Suppose I don't care much about the nice versus the cheap hotel, but the current prices are low, so I start bidding for the nice rooms for all the nights of my stay. And remember, I can't switch hotels during mid-trip. Now imagine that the nice rooms start to skyrocket. I could drop out of the skyrocketing auction, but then I'm stuck with the one. Suppose I'm winning another room, I'm stuck with it. I can't use it unless I get all of them. That's why the complementarity can really kill you. If I'd predicted which rooms would get expensive, then I could have rearranged my trip when the flights were still cheap, or just bid for the cheap hotel from the start. So price prediction is key. And we've done a whole study on price prediction in this domain. And just briefly, the conclusion there, our strategy does using this simple Walrasian economic model with no historical data at all does as well as the most sophisticated machine learning approaches using historical data. But back to the game methodology, how this applies to TAC. Just like in FPSB, where we started with truthful bidding and parameterized it, generalized it with parameters, we do the same thing here. Our baseline strategy now is this Walrasian price predictor. And then we introduce parameters like variations on hotel bid shading, for example, introducing a shade factor, just like we did with FPSB, or other ways to do shading in hotel auctions. Different entertainment strategies can be swapped in and out parametrically. We have this complicated decision process for buying flights, for the timing of buying flights, that we parameterize with a few thresholds. But the conclusion is we end up with a bunch of parameters. We sample very sparsely from that space and come up with 40 candidate strategies for Wolverine. With 40 strategies in the full 8-player game, there are hundreds of millions of possible profiles, and this is where the player reduction is really critical. We really decided it was completely hopeless. Each game takes 12 minutes, by the way, to simulate. So we've had a test bed, a cluster of servers running these games with variants of our Wolverine, playing against itself 24/7 for over a year. But even doing that, the full game was just out of reach. We can sample a very small fraction of the profiles in the 4-player reduced game. The 2-player game we can get a much better handle on. The 1-player game we can get a great handle on, but that defeats the whole purpose. There's no strategic interaction then. OK, so I'll just gloss over how we use this to come up with our final strategy to actually play in the tournament. But we did the game analysis on these empirically determined payoff matrices, came up with some metrics to rank the various strategies. We actually tried them in the seeding rounds and the qualifying rounds of the tournament to see how they really did against the actual other players. And conclusion, Wolverine officially came in third this year. But I just have to mention, if you notice these 2 0 games and 10 0 games there was some various technical difficulties, and the organizers of the competition actually published these unofficial results, unfortunately unofficial, where we kicked butt at the significance level, p equals 0.17. So, OK, so to sum up, the strategy generation. The very first part of this was the algorithm I described for best response strategies for infinite games of incomplete information. The next big piece for games that don't fit that class of games, either have more than 2 players, have multiple rounds, is this empirical game methodology for applying this game-theoretic analysis to much larger games than previously possible. I talked about theoretical and experimental evidence, focused on FPSB and applying the empirical game methodology to FPSB, even though we didn't need to, since we solved that game, solved the analytic version. Then the real application of it was to the trading agent competition, where we started with our price prediction approach to strategy generation in simultaneous auctions for complementary goods, parameterized that baseline strategy, and then applied the empirical game methodology to come up with a good variant on that to play in the trading agent competition, and found it did very well. OK, that concludes my talk. So are we switching off for questions, or?
Do anyone have any general questions?
When you're playing the games against each other, it sounds like you're trying to play all possible parameters against all possible parameters, which gives you a very big explosion.
Right.
I was wondering if there's any way to sort of play sort of representative samples or random samples against each other and determine
That's
what
actually what we did.
parameters
So if you remember here, we came up with this fairly rich parameter space, and that actually had millions, essentially unlimited number of possible games, and that is completely hopeless to try to simulate something for every possible strategy profile. And so this was really done in a very kind of ad hoc way to just pare it down to 40 representative points in this attribute space. So it's an extremely sparse sampling of the space. This was kind of done semi-manually as we gathered data and we kind of saw which strategies were tending to do well, and we'd introduce variations on those. So actually the next big piece of future work is actually to kind of automate that process. Actually trying every possible profile of strategies is not realistic at all, but we do want to automate the process of picking them. So these 40 were picked semi-manually as we just watched the experiments unfold. But of course for FPSB, what we did, just by picking the right level of discretization, remember here, this is discretizing by 40ths, and this is playing every possible profile against each other. And we can do that even though this gets into millions and millions of games, because each sample we do is essentially instantaneous. So it's a very drastic difference from the training agent competition, where every single sample takes 12 minutes. Other general questions? Okay, thanks.